Okay, everyone. The final talk in this session's going to be given by Chung Piaw, who is at the National University of Singapore. Chung Piaw, I've been having a little bit of a look at your website, and it's quite clear that you've got a lot of very senior responsibilities, or have had, both in your university, but also in the community, the OR community more generally. So you're obviously doing a lot, and you've got a lot of interesting research achievements. And so one of them's online flow control, and you're going to tell us about it now. So I'm looking forward to it, and I'll hand over the screen to you.
Thank you, Peter. Yeah. I want to thank Peter, Michelle, and Nikki for the invitation to speak. I happen to be traveling in Geneva now, actually. So I'm giving the talk from the hotel. I'm hoping that the Wi-Fi can sustain the intensity of this talk. Let me start by telling you more about this topic that I'm talking about. So instead of the talk will be based on a paper that I've written with a number of people in transportation, Jingpen, Gao Ziyu, both from China, and also Guotong now in Hong Kong, UST. It's about this body of work on online flow control. So it's related to Xingwin's earlier talk on online optimization. But instead of learning, we are looking at the multi-objective stochastic DP. So I want to present a new way to connect the online optimization mindset with the multi-objective stochastic DP. And instead of the stochastic gradient descent type arguments, I will try to do the connection using the classical Blackwell's approachability theorems. So it will be, I hope it will be something of interest to the community here. Now let me start by talking about a few use cases on online flow control. This is a problem that you encounter in many operational problems. But let me start with this problem that the Singapore government actually came to the Institute of Operation Research and Analytics for help about 2 years ago. That was at the height of the vaccination exercise. The government, the Ministry of Health then was tasked to manage the vaccination exercise. So they have set up a series of vaccination stations all over the island, trying to get the citizens to go to the vaccination stations to get their vaccination jab, and the Singapore government decided to use an appointment system. So in order to get the vaccination, you need to go to this online system to make a booking. Now the problem is interesting in this case because the vaccine supply at that stage was fairly erratic. So the Singapore case started with Pfizer and Moderna. And you see that there are actually periodic supply of the vaccine into the country. The number I can't share, but the schedule is fairly erratic and subject to lots of changes. But at the same time, at that point in time, the Singapore government was still adhering to this very strict interval between successive vaccination. The first dose and the second dose for Pfizer must be 3 weeks, and Moderna must be 4 weeks, so on and so forth. So the problem, operational problem that they were looking at is essentially a real-time flow control type problems. At any point in time, the ministry needs to decide how many, which group of the population to call up for vaccination, and how do they invite these people to book in the national appointment systems to get slots for their jabs in the vaccination centers. So you see that the problem then was, how do you release the appointment slots to the citizens in such a way that you want to make sure that the demand doesn't overwhelm the uncertain supply. And yet you want to make sure that you always have enough vaccines for the second dose. So if you invite too many people to come for the first dose, you will see that these people may use up all the available vaccines. And if there's any disruptions to the supply, a lot of people will not be able to get their second dose vaccination. So the challenge is to deal with these operational constraints, and yet the goal is to maximize the rate of vaccination. So there's a national agenda to get as many of the citizens vaccinated to finish their second dose in as short a time as possible. So that was the gist of this problem, and the ministry was essentially looking at this as an online flow control problem. Online in the sense that almost every week they will review the status. They look at how many people have signed up. For example, you see that they were essentially using Excel spreadsheet to do the real-time control. They look at how many have booked, how many vaccine has arrived, and the total availability. So supply on hand minus the number of slots in the appointment systems, indicating that they are short of about 30,000. So in every week, the ministry was solving this kind of online flow control type problem in order to use the release of the appointment slots to regulate the flow through the appointment systems. So this is one example of an online flow control problems, and you can see that is essentially a stochastic DP type problem, but it's also a multi-objective type, because other than the rate of vaccinations, there are also other issues about not asking the citizens to wait for too long. So you need to time your invitation schedule in such a way that when the citizens go to the appointment system, they will be able to get their desired slots in the shortest possible time. So the flow control problem has to balance all these side objectives on top of maximizing the rate of vaccination. Now, another problem, of course, is I think is also addressed by many scholars. Is about the allocation of essential critical care resources to patients, like ICU, like oxygen tanks. And you see there are a lot of allocation methods being proposed. But in this problem, you can see that the challenge is about allocating all these reusable resources to patients with different needs. So there have been many methods being proposed, many objectives in this kind of allocation problem, whether to maximize the number of lives saved, or to maximize the number of life years saved, or to a certain extent simply use lottery methods in order to ensure that the outcome will be fair to the patients. So there are if you look at this kind of allocation problem, in a nutshell, is a flow control problem, because at any point in time, you realize you have a set of oxygen tanks or ICU beds available. You also have a set of demands waiting in the system for to receive some of these resources. And the challenge in the online setting is to determine the allocation, taking into account that the demand arrival coming in the future, the usage rate of the patients who are currently on the oxygen tank, so on and so forth. So it's again a fairly complex stochastic dynamic problem, and essentially a multi-objective one. So this paper is about something that we saw in this kind of problems. But of course, I'm working with transportation scholars. So I will be talking about this use case in Beijing, about the rush hour congestions, about trying to regulate the flow in the metro stations in one of the Beijing highest traffic, the heavily congested metro station line. But this rush hour congestion is a common problem in many urban cities, and not only in Beijing. You see this problem in Tokyo, Mumbai, and the transport authorities have been looking for ways to deal with the congestion problems. The risk is quite clear. Risk of potential stampede or even passengers complaining about unfair service experience. So if in some crowded stations, you see that the capacity of the train is basically fully used up at the first station, leading to the fact that passengers at the second, third, or fourth station may have to queue for a long time in order to board the train. So they were looking for solutions to do this kind of control type problem. At the higher level, this problem can only be achieved by expanding the capacity. Or in some cities, they were trying to do demand management by introducing incentive to move demand away from the peak hour commute. I will not go into all these demand management or capacity expansion literature, but focus this talk on the passenger flow control. So essentially, you can view the train as scarce resources, and the real questions is how do I do emission control to make sure that the capacity will be well utilized. Well utilized in the sense you can measure the performance based on efficiency. That means you want to enable the most number of passengers to board the train to go about to do their business. Or you can also try to maintain some level of fairness, ensure that for different starting station and ending stations, that the customers within this OD leg will be served at certain acceptable service level. So you want to maintain equitable service level for all the OD pairs within the transportation systems. So we call this the type 2 service level, to measure the so-called the service level attributed to each OD pair. I will go into the definition later, but let me use a small example to illustrate this problem. So this is a small problem with 4 stations, and you see that the train moved from station 1 to 2 to 3 to 4 with a capacity of about 100 seats, and the dotted lines here shows the demand of the OD pair. So you have this kind of demand scenario in a train moving from 1 to 4 with capacity of 100. Now, if you were to use a first come, first serve policy, no control, then you will see that immediately from the first station, 100 customers would have boarded. And you will see that from station 2 to station 3, there are a lot of customers requesting short trips, but these customers were blocked because all the seats were used up before the train reached station 2, and nobody alighted in station 2. So the segment OD 2 and 3 is completely blocked. OD 3 and 4, by station 3, you see that 50 has alighted. So only 50 out of 100 from station 3 to 4 can board the train. So if you were to leave it to the first come, first serve policy, you see this uneven allocation. So the key question is whether there's a better way to do emission control in this kind of service system with reusable capacity. And of course, how do you do it in such a way when the OD demands are stochastic and random? Of course, the one way to solve this problem, especially in the stochastic sense, is to use DP techniques. So you can solve this problem in many ways. One way is to use, assuming that the demand are deterministic, solve a dynamic program to maximize the number of passenger carried or the revenue generated. So this is what we call the RMP algo. Or you can think about using a DP to solve this problem with fuel rate guarantee. So, for example, your objective could be to maximize the minimum fuel rate. Fuel rate measurement is basically a measurement of the demand fuel over the demand requested. So, for example, just now I mentioned, if you were to use the first come first serve policy from 1 to 3 and 1 to 4, you'll be able to carry 50 customers each, and the fill rate is 50 out of 50 for 1-3 and 50 out of 50 for 1-4. So you have a fill rate of 1. But for 2 to 3, unfortunately, you cannot. The first come first serve doesn't carry any passengers. 100 requested, so the fill rate is 0. 3 to 4, 50 boarded the train. 50 out of 100 boarded the train, so the fuel rate is about 0.5. So if you look at the aggregate system performance for first come first serve is 150, and if you look at the minimal fuel rate across all the different OD pair, some OD pair receive 0% fuel rate, some OD pair receive 100%, but the minimum is about 0. Of course, the first come first serve is not revenue maximizing. So if you were to focus on maximizing the number carried, you would have say no to all the customers in the first station, leaving the capacity for 2 to 3 and 3 to 4, and that allows you to carry 200 passengers. But again, of course, the fuel rate is 0. On the other hand, if you were to do a max mean fuel rate type policies, you see that the DP will give you a solution like carry 25 from 1 to 3, 25 from 1 to 4, 50 from 2 to 3, 75 from 3 to 4, leading a total load of about 175 and a minimal fuel rate of 0.5. So you see that the fairness by paying attention to maximize minimal fuel rate, surprisingly, this policy already beats the first come first serve. So that in terms of the load carried and in terms of the max mean fuel rate, so the fairness mindset actually helps to improve the performance of these systems compared to the first come first serve. So this is the example driving our, in fact, this line of work. So the key questions we have been asking over the years is how do we incorporate this service mindset into service level mindset into the capacity allocation type algo in order to improve the performance of the systems. Now, of course, in transportation, especially in this kind of metro stations, one of the key limitation, key bottleneck in the use of all these sophisticated online flow control type techniques is basically the information technology structures, like counting the number of passengers in the metro station itself was before for up to a few years ago was still impossible. But of course now we know we have tons of fancy AI startups with technology to do people count using video analytics and so on and so forth. So this kind of flow control using real-time demand information, giving the decision makers a glimpse of the state of the system in real time is now feasible. Like in the appointment system that I mentioned earlier, the decision makers has in his possession the number of slots that will come in the future, and also the number of vaccines in the system. So the supply and demand info are known before the decision maker make its decision. So we need the same kind of environment in the metro station setting. And the point here is that this kind of environment is readily available. So I don't know. Let me quickly go through the leak review. In the transportation side, this metro system oversaturation problem has been looked at by a host of scholars. They look at the timetable optimization. There were some studies that look at demand management, and there's some recent studies on static passenger flow control. So these are not real time. So these are just the paper essentially solve static optimization problems. So there's no sort of revision to decisions in an online or dynamic setting. So it's not a dynamic type of passenger control problem. So the paper that we have is arguably the first in the transportation area to look at a dynamic type problem. And we are able to do this essentially by combining some of the results in two areas, like revenue management. This real-time dynamic control has been used for a long time, but very often you see that there's actually no fairness consideration. So the sole focus in a lot of this paper is essentially to maximize revenue. At the same time, in the supply chain area, there are a number of work that talks about service level constraints and how to use, based on service level constraints, to allocate resources. So we have done a number of papers in this area. I guess one of the goals in writing this paper with Gao Ziyu, Jingpen, and Guotong is to find a way to integrate these two areas together. You see that revenue management, you have a single objective to maximize revenue, whereas in the fuel rate constraints supply chain setting, you have a host of site constraints that you need to fulfill in order to serve the customers. So how do we combine the two together? So this paper is essentially about a very simple way to use what is developed in the supply chain area to solve the revenue management problem. So let me formally define the online passenger flow control problem in this particular setting. So we have a train with capacity of S moving from station 1 to N. And we also have the OD demand from I to J, station I to station J. And the information is reviewed only sequentially during the journey. So you only know the IJ demand information when you reach station I. But of course, when you're at station 1 or even station I-1, when you do your emission control, you need to bring in the demand projection at station I. So in station 1, you see only a random, the demand at station I is a random number. But once you reach station I, the demand in station I is realized, and you need to make an online emission control decision based on the actual demand at I. So this is a DP problems, and the objective is to maximize the expected number of passengers carried. Okay, so this is, you can view this as a simple DP problem. And I want to apologize for the notation, but essentially, if you set up the DP state transition, you essentially at every station I, you need to do an emission control. You need to decide XIJD. So for every ODI starting from I to J, you need to decide how many demand to serve, given that you know that the DIJ. So DIJ is realized at station I, and the XIJ is essentially a decision that you make. How many % of this DIJ do you want to emit onto the train? And of course, the emission decision is constrained by the capacity and who else is still on the train. Those who boarded before station I and whose destination is after station I. Objective is to maximize the total number of people carried in this journey, and we have also fuel rate constraints in the sense that the XIJD, the emission control policy, must ensure that at least a beta IJ proportion of the demands are served. So there's this service level fuel rate type consideration imposed into the DP. So you can view this as a stochastic DP with site constraint. And these site constraints complicates the DP type problem. Of course, if you look carefully at this problem, if my beta IJ is a free variable, I can choose beta IJ freely. The objective function can be recast as a service level constraint problem if I choose my beta to be one that maximizes the expected revenue. So you can, if you choose the beta correctly, the revenue maximization problem is essentially a service level constraint type problem. So, if anyone that is feasible for this service level constraint problems will automatically attain the maximizing revenue maximization targets. So now, of course, you may see that the imposition of the fill rate requirements complicates the revenue management problem. But I actually want to argue in this talk that actually the service level constraint actually give you a new perspective to solving the classical revenue management problem in the following sense. So I want to talk about some of the earlier work that we have done in this space about having the advantage, having service level targets in online flow control. So the analogy is like catching a ball. A lot of the time when we solve stochastic optimization problem, we set up elaborate mathematical models, and then we say that this is the optimal policy, optimal solution. Like catching a ball. I mean, if you use the optimization mindset, basically, the problem reduces to getting the initial condition of the ball and looking at the force of gravitation, study the dynamics of the path of this ball, and then try to predict where the ball will land, and run to that place to catch the ball. So the optimization problem, if you were to solve this ball catching problem, is like predicting where the ball will land next. But we know that in practice, we don't solve the ball catching problem this way. Humans devise heuristic, and in fact, we use real-time information of the location of the ball. So most people catch the ball by fixing their gaze on the ball, knowing where the ball is, and use a kind of very simple heuristic. Like one heuristic is a gazing heuristic. You look at you try to fix your gaze at the ball at a constant angle alpha, and then start running towards the ball, adjusting your running speed. This is your action taken online by tracking the distance from your real-time position to the ball so that the angle of the gaze remain constant. So most humans solve this problem by this gazing heuristic. When the ball position changes, you adjust your body positions in such a way that you try to always maintain a constant angle of gaze until you catch the ball. So this is a heuristic used not only by humans, but also by birds, by animals to catch their prey in motion. In fact, some of the missiles, according to this paper, was actually the missile used by the Air Force actually also use the gaze heuristics to try to bomb a moving target. And this heuristic was proven to be very effective during World War II, and when the Royal Air Force actually uncovered these heuristics to catch the enemy planes. So the gazing heuristic has been used in many interesting settings. And my proposition is a lot of the online type algo can be seen in this way. We are fixing the gaze, and this is where the service level comes in. If you have a clear view on the service level targets that you want to attain for all the OD pair, you can actually use a service level as the alpha to allow you to adjust your position. You adjust your positions by choosing your allocation, and your allocation decision should be chosen in such a way that every time when you see deficiency, you do allocation so that you improve a little bit. You move closer to your targets in a small but steady steps. So the earlier work that we have been doing essentially is about using these gazing ideas. So the first paper we wrote was paper that talks about finding the minimum capacity needed to deliver a guaranteed type 2 fill rate service level to all the different customers. So this happened to be an unsolved problems in the supply chain area. So we essentially used the gazing heuristic, which the proof that this kind of heuristic using gazing works is essentially a Blackwell's type argument. So it connects the gazing heuristic with these classical results. And the second paper essentially allows us to extend the theory to talk about service level in a network setting. So when you have flexibility, when you have when you can choose to use your resource to serve different type of customers, how do you do it in a coordinated manner to ensure that all your customers will be given adequate service? And this also related to adaptive knapsack problem. So if you were to pack your knapsack, how do you decide what items to pack into the knapsack next if the weights and the profits are also stochastic? So this gazing heuristics, once you have a service level target in mind, you essentially can use the gazing heuristics to sort of design your online allocations. And one of the use case that we have worked on is actually a problem from TT about trying to use this gazing heuristic to do real-time matching in a right. So this is the problem setting. You have we did this study in China, but I show you here what we are trying to replicate in Singapore. So you have taxis moving around the cities, and you have passengers demand. So you see people calling out for taxis. So one of the problems that the ride-hailing companies need to solve is to determine who to assign, which drivers assign to serve which customers. And this assignment decisions is actually non-trivial because it's essentially a multi-objective type of problems, because do you assign the nearest driver to the passengers so that the weight of the passengers is the shortest, or do you assign a better drivers? All the drivers come with quality ratings. So do you try to assign the better drivers to the customers? So designing this assignment logic turns out to be a big challenge in many ride-hailing companies. You see a trade-off. And in fact, this company that we work with did some A/B tests and indeed verified that the quality of service actually has a lot of impact on their business. You see in one city they did A/B tests, and in one city they assign good drivers to customers. Another cities they use existing logic, and they saw a drop in the complaints rates. If they were to assign good drivers to the passengers. So the assignment of drivers, quality, and also the waiting time has a lot of impact on the performance of the systems. So the paper, the applied paper that we are writing is still a working paper. Is essentially a paper that propose the use of this gazing heuristic to do the assignment. Essentially, you have different objectives, and you give a target to all your different objectives. So when you were to do the assignment, you try to check among your objectives which one is losing ground, and try to assign more weights to catch up on the objectives. So this is a kind of dynamic weighting functions to allow you to catch up, to make up on the objective. And one of the interesting things that we saw in this study is that essentially in the IID setting, if you were to view the ride-hailing problems as solving a sequence of matching problems with multiple objectives, then one of the interesting insights is that if you were to use the gazing heuristic to do this assignment, somehow the selection of the targets, like for example, you may choose a utopia point, you have multiple objectives. If you try to optimize the objective in single dimension, and you may get the utopia point. This is the ideal point. In every dimension, you have the maximum performance. You may want to use this as your starting target to drive your online allocation. But it turned out that, of course, in your final performance, you will not be able to reach this utopia point. But in some kind of online allocation, if you fix your gazing heuristic correctly, and especially in the IID case, you can show that the online solution actually converges to this what the economists call the compromise solutions, which is the solution closest to the utopia point by Euclidean distance. Of course, there are a host of other techniques being proposed to solve this kind of online assignment problems. Some leads to a dominated solution. Some leads to a solution on the Pareto frontier, but maybe far away from the utopia point. So the interesting thing is you can hit the compromise solutions through this sequence of adjustment to your positions. So this is some of the main findings. But of course, the theory at that point in time was still handicapped by the fact that we need the problems to be IID. So the purpose of this paper that we have written is to extend this theory to deal with dynamic programming cases. How do we use gazing heuristics to solve stochastic DP with multiple objectives? So recall that this is the problem that we are motivating problems. And we want to solve this stochastic DP with this few rate requirement constraints. The first result inherited from the Blackwell's approachability theorem is actually this result that says that essentially it says that the multi-objective problem can be reduced to a single objective problem in this using this kind of gazing type heuristics, and this is nothing but the aggregation of your service level constraint. Imagine you have a service level constraint stochastic DP problem. If I aggregate the constraints or the IJ, each pair of OD pair has a service level constraint. So if I use theta IJ, which is freely chosen, if I use theta IJ to aggregate one side of the service level constraint, I would have this. And aggregation on the other side will lead to this kind of problem. And this result essentially says that if no matter how you aggregate your service level constraint together, if there's always a way to find a policy to maximize the expected attainment on this on the box objective in the box, and the maximum is always larger than this service level constraint, then you can guarantee that you can find an allocation that meets all the multiple objective service level constraints. So essentially, these theorems allow you to collapse all the multiple objective in the full rate constraint into a single objective weighted by the theta ij. If you look carefully at the inner maximization problem, this is essentially a single objective DP with the revenue given by theta ig. So the key insight from this analysis is that the multiple objective stochastic DP problem can be reduced to a single objective DP problem if you can do this in an online setting. So the online setting helps to connect the single objective and the multi-objective stochastic DP type problems. And the idea is the heuristic, the algorithm is actually quite simple. So the algo that we do the allocation is based on this concept of depth. So the depth is basically the something from the gazing heuristic. You wanted to attain a Fourier target of beta ij prime, And so if you look at the historical performance up to Apple 10, suppose this is the realized performance. So if you are still below your service level target, you call this a debt. So you have a debt, which is the RIG, and the weight for the pair IJ at time t plus 1 is simply the average of all the debt that you owe the customers up to time t. And of course, that may be negative. So we set this to reset to 0 if it is negative, and then use the alpha ij t plus 1 as the new weight functions to run the DP. So in a way, you can run the DP with different weights, alpha 1, and from alpha 1 and the performance in your first problem, you determine your debt, and then you get your alpha 2, and with your alpha 2, you run your DP and you resolve until you get your alpha t. So in this way, you get a sequence of alpha, which is the relative weights for your DP. And amazingly, if you were to do this in this way, if you were to choose your alpha, remember you have alpha 1 up to alpha capital T from this DAA policy. As you run the simulations, you get the alpha based on the gazing heuristic, and you were to choose one of these alpha randomly and use this random alpha to run real-time flow control type problems. You can show that essentially you get the desired performance, the expected performance using this kind of online allocation policy ensures that if your T is big enough, so if your T is if you run the offline simulation long enough, you can ensure that you can use the alpha chosen this way in an online setting so that the performance is at least within epsilon of your desired performance target. So this is one of the key results that allow us to tie the stochastic DP with multiple constraints into solving it essentially with just one objective functions. Now, I don't think I have time to go into the proof. So the proof of sufficiency is essentially the argument using standard Differential duality and then invoke Blackwell approachability theorem. So this is a step that we have followed in the earlier paper that we have published, but so I will not repeat here. But the key observation is the first part that's saying that even in a DP setting, we can apply the same logic to get the conclusion. This conclusion is fairly important because it says that if we were to use the debt-based policy to do the allocation, then the expected level of your debt weighted by your alpha ijt plus 1 is actually less than or equal to 0. So you can, and for those who know Blackwell, the fact that the expected debt reaches 0 ensures that the decision maker has a strategy to guide the performance into the appropriate non-negative octants with high probability. So this is the angle that connect the gazing heuristics with the performance. Of course, so far I've been talking about service level fill rate target, but these techniques can also be used to incorporate other kind of targets like revenue targets. So you have revenues RIJ for the OD pair RIJ. You can actually set yourself a target, say that you want the expected revenue to be at least Z, and then add this into your service level constraint type systems. So the same ideas by adding revenue as the target and use this to target to drive the allocations policy can be easily extended to deal with different kind of constraints. So if you have other than the fill rate constraints, if you have also the service level constraints, Now, in numerical experiment, we've realized that the way you scale the service level constraint is also quite important for performance because otherwise the service level constraint may be at different scale. If they are at different scale, you'll find that the service level, the gauging heuristic may not work as well because if one objective dominates, it will be very difficult for you to adjust your positions. So we need some scaling to make sure that all the service level constraints are around the same scale. So we use the M to normalize. And with this, you'll find that the same idea can be used to collapse. Right now, I have n choose 2 plus 1 target, service level targets. But by using the notion of depth, I can collapse the targets into a single objective type stochastic DP problems. So this again allow us to extend the theory to say that even if you want to serve the customers with the desired beta ij service level fill rate, and if you want to maximize revenue at the same time, you can do so by searching over Z. So once you fix Z, the algo will be able to tell you whether the targets are attainable. So this is can be achieved by a line search. Now we have done this comparison. Let me show you some simple numerical results just to give you a sense of how this idea perform in numbers in computational experiments. So what we do is basically we have of course random demand. These are the parameters for the random demand. DIGs are the demand, number of customers moving from I to J, and of course to start the algo, we need to have fill rate targets. So there are many ways to add fill rate targets to the policy. One way is to use the training data, generate samples, and then solve offline type problems to get your service level targets, so that the service level targets can drive your policy, the depth-based policy. And you can see that. So once we fix the service level targets, you can then use hindsight. Hindsight optimal means you know exactly in the online setting, you exactly knows how many will be coming in the future. And if you solve the hindsight optimal, you get on average this kind of performance, 185. But the depth-based policy without hindsight, so you essentially use the service level to drive you to a good revenue management performance, already get you about 182. First come, first serve performs very poorly in our numbers. We also compare this against some of the online allocation algo that talks about IID case. So the DP, the nice thing about the DP, especially in this setting when the capacity is reusable, it doesn't agree with the setting in Chung, but the algo, you can see that incorporating the DP and moving away from IID to non-stationary environment actually helps in terms of the performance, whether it is the revenue management optimization perspective or the fill rate perspective. Okay. And we have also done a test on this data set in Beijing, Metro number 5. I was told by my colleagues that this is one of the most heavily used metro station, at least in Beijing. And you see the arrival rates of passengers across time during the early morning peak hour. This is the mean demand rates at different times. Some hitting close to 6,000. Coming from Singapore, this is a mega number. And we do the allocation in two settings. One is differentiated in the sense I have a different service level for different IJ. So this is assuming that I know the destination at station I know where the customers is traveling to, and I do emission control based on this IJ pair. Undifferentiated setting means I only know that the customers come to station I. I have no control. I do not know where the customers will be arriving. So this is the undifferentiated setting. And I think the numerical experiment using the data, at least the demand profile from this line, shows clearly that the first come first serve is not comparable to this kind of service level differentiated type planning system. If you look at the objective value, if you can differentiate the OD and do emission control based on this differentiated setting, the improvement is quite substantial. Depending on the fuel rate targets that you offer to you want to maintain in your systems, anything beyond this 0.47, 0.46 is unattainable given the capacity of the train. And the objective values, you can see the clear dominance, and even the Gini coefficients. In terms of fairness, we use Gini coefficients to measure whether the service delivery is fair to the passengers. And you can see the first come first serve is dominated. So apparently the Beijing government was using first come first serve to do this kind of gate control at that point in time. So this study basically showed that the more sophisticated kind of emission control can be solved and put to good use. So the rest are basically just some of the service level measurement from the metro station perspective. So if you were to use the gazing heuristic to do the emission control versus the first come first serve, what is the service experience at the station level? And also what is the service experience for passengers with different travel distance? You can see that, for example, the differentiated and undifferentiated setting, you can see that fuel rate, these are the number accepted, these are the fuel rate. The point you need to pay attention is the differentiated RMH. So this is the orange triangle pointing up. You can see that it's always at the most of the travel distance is always on the higher end compared to many of the other kind of policies. Also revenue at different point in time. So the gazing heuristics to do emission control seems fairly promising. Of course, right now we are extending the study to multiple train, but the real challenge in multiple train in online emission control is you need to monitor if some passengers will come early and could not get onto the bus, so they may have to wait for the next train before they can board the train. And this waiting time, if you incorporate this waiting time, then the online emission control, you need to coordinate the emission control policies across multiple trains, and you need to capture the waiting time. So we are right now trying to develop, extend the emission control algo to deal with this setting. Yeah. Anyway, there are also other ways to extend this. I use service level to discuss the problem, but we believe that the whole mindset about using service level target and from the service level target determine your allocation control policies based on the gazing heuristic is a promising one. So I will not talk about the other extension, but maybe I can stop here to take questions. Okay.